When studying Green's theorem, we found that if we integrated the Green operator of a two-dimensional vector field over a two-dimensional domain, then what we were really doing was calculating the work done by that vector field on the boundary of that domain. Well, that's a story that happens in 2 dimensions, but we could certainly imagine a similar story unfolding in 3 dimensions. In 3 dimensions, one studies surfaces, so it's natural now to ask, well, what happens when we integrate a vector field over a surface, and does that somehow relate to the work done by that vector field on the boundary of the surface? What we'll find is that there's an analogy in 3 dimensions to Green's theorem called Stokes' theorem. So you'll find that this lecture sort of mirrors the structure of Green's theorem, because Stokes' theorem really is the 3-dimensional version of Green's theorem. So that being said, let's start by discussing boundaries in 3 dimensions. So let's say that we're studying a surface called S in R3. By definition, the boundary, which is denoted the same way, which is to write the partial sign of the surface, is the outer edge of the surface. So if our surface looks something like this figure, the boundary would be the outer edge, which is highlighted in red here. So the first thing to notice is that for a surface in 3 dimensions, the boundary is the union of simple closed curves. So here we're looking at a figure where the surface we're studying is maybe a cylinder where the top is tilted a little bit. Well, the boundary of this region looks like it has 2 parts. There's the bottom circle, which is part of the boundary, and this top ellipse maybe, which is part of the boundary. So maybe the bottom is called C1 and the top is called C2. In this situation, what we would write is the boundary of S, so partial of S, is C1 union C2. Now, remember in the statement of, or when studying Green's theorem, once we developed the notion of the boundary of a 2-dimensional domain, we then stated what it meant for that boundary to have positive or negative orientation. And the situation was determined by the domain's location relative to the unit tangent vector of a parameterization of the boundary. In 3 dimensions, the story is a little bit more complicated because there's a little bit more room to work with, but there still is a definition of positive and negative orientation for surfaces in 3 dimensions. So it turns out that the location of the surface relative to the standard normal vector and the unit tangent vector gives the orientation of the boundary. So whenever we parameterize a surface, our parameterization defines the standard normal vector. Well, what we do to establish orientation of the boundary is we imagine that the standard normal vector is sort of dragged up to the outer edge. And so here on this figure on the left, we're looking at a paraboloid where the standard normal at the origin is pointing up. And when we drag the standard normal out to the boundary of this paraboloid, the standard normal is sort of pointing into the surface. And the idea is that at that point, in the configuration here on the left, the unit tangent is sort of pointing into the figure. So if we imagine ourselves being the standard normal vector, where our feet are at where the vector emanates from, and our head is the tail of the vector, when we look in the direction of the unit tangent in this figure on the left, the surface is to our left, which means that the orientation here is positive. In the figure on the right here, the situation is exactly the opposite. So we have the same choice of our standard normal vector, but the boundary here is parameterized in the opposite direction. So here, if we were the standard normal vector, where our feet were at the where the vector emanates from, and our head is where the tail of the vector is, When we look in the direction of the unit tangent vector, the surface is to our right, not to our left, which means that the boundary here is negatively oriented. And of course, each part of the boundary must be inspected to determine orientation. So here we have the same surface with the same choice of normal vector in both of these examples, but here the boundary portions are parametrized with different orientations. So if we look at this figure on the left, our figure here is a cylindrical region where the normal vector is pointing into the cylinder. Again, if we imagine ourselves being the normal vector here, when we walk up to the outer edge of the boundary, we find that the surface itself is to the left, not to the right. But here on the right, when we walk up to each part of the boundary, we find that the surface is to the right, not to the left. So the conclusion is that for the surface on the left, the boundary is positively oriented, whereas for the surface on the right, the boundary is negatively oriented. And of course, the choice of the direction of the normal vector influences the orientation. So here we have the same example from the previous slide with the same orientations on the boundary, except we flipped the direction of the standard normal vector. So now in both of these examples, the standard normal vector is pointing out of the cylinder, not into it. Well, if we, in the example on the left, if we move this standard normal to the edge or to the boundary of the surface, on the left here we find that the surface is to the right of the normal vector, not to the left. And on the right example here, we find that if we move our normal vector to the boundary, we find that the surface is to the left of the normal vector, not to the right. So on the left, by switching the direction of the normal vector, we've changed the orientation from positive to negative. And on the right here, by switching the normal vector, or the direction of the normal vector, we change the orientation of the boundary from negative to positive. So the convention we adopt is the same convention we adopt when studying Green's theorem. Unless otherwise stated, we always assume that the boundary of our surface is positively oriented. And by assuming that the boundaries are always positively oriented, we then allow ourselves to do arithmetic with boundary curves. So here we have an example of a cylinder that's parameterized in such a way that the standard normal is pointing out of the cylinder, not into it. And we have two boundary curves in this scenario, one called C1 at the bottom and another called C2 at the top. Well, we've chosen parameterizations of these boundary curves, but we need to check whether or not these parameterizations are compatible with our positive orientation as a convention. So if we look at first the bottom boundary curve, we imagine moving the normal vector down to that curve and then looking in the direction of the unit tangent. In this case, at the bottom, when we look in the direction of the unit tangent, the surface is to our left, which means that the bottom parameterization is the positive parameterization. The situation is different if we move the normal vector to the top boundary curve. When we move the normal to the top boundary curve and look in the direction of the unit tangent, the surface is to our right, not to our left. So the top boundary curve has the negative orientation. So what we would write here is that the boundary of our surface is the first boundary curve, C1, minus the second boundary curve, C2. This is because the boundary curve C1 respects the positive orientation, and the boundary curve C2 has the negative orientation, which is why we're subtracting it. Okay, so the context in which we care about all of this is the context where we have a surface, but we also have a vector field defined on the surface. In a scenario like this, we define the circulation of that vector field around the surface to be the line integral of that vector field along the boundary of the surface. In other words, the circulation of a vector field around a surface is the work done by that vector field on the boundary of the surface. And one important thing to note is that circulation integrals respect boundary arithmetic. Since we always assume the positive orientation, we have to account for that positive orientation when we calculate circulation. So here we have the figure from our previous example where the bottom boundary curve had the positive orientation and the top boundary curve had the negative orientation. Well, if we wanted to calculate circulation in this scenario, we would need to calculate circulation on each part of the boundary individually. So we would need to do a line integral of the vector field over the first boundary curve C1, and we would also need to do a line integral of the vector field over the second boundary curve C2. But since the first boundary curve has the positive orientation, we add the first line integral. And since the second boundary curve has the negative orientation, we need to subtract the second line integral. So let's do an example of a direct circulation calculation. So here we have the data of a surface S, which is this cylinder. This cylinder is defined by the equation x squared plus y squared equals 1. So here we have a cylinder with radius 1. And it's bounded by z equals 0 and z equals 4. So at the bottom of the cylinder, we're looking at the circle of radius 1 in the xy plane. And at the top of this cylinder, we're looking at the circle of radius 1 in the plane z equals 4. Note that in this example, we've placed our orientations along both of the boundary curves so that we respect the positive orientation induced by our choice of a normal vector in this example. Here we're studying the vector field f, whose coordinates are x times y, and 2 times x times z, and x times y. And the units here are newtons on our vector field. Well, let's look at parametrizations along these boundary curves. At the top here, our boundary curve is the circle of radius 1 in the plane z equals 4. And if we were to look down on this circle, we would see that the orientation is counterclockwise, which means that we can parametrize the top of this boundary by using the standard parametrization of the unit circle, and then we tack on z equals 4 on that parametrization. So the parametrization of the top part of our boundary is cosine t, sine t, 4. For the bottom part of the boundary, we have to be a little bit more careful. For the bottom part of the boundary, if we were to look down on it from the z-axis, we would be looking at a parametrization of the unit circle in the clockwise direction. So here, we'll parametrize with x bottom, having coordinates cosine of negative t, sine of negative t, 0. So we're replacing t with negative t in our standard parametrization of the unit circle to account for this change in orientation. Now that we have our parametrizations, we can calculate the work done by this vector field on each part of the boundary of this region. So to calculate the work done by this vector field on the top part of the boundary, what we do is we just apply the formula for line integrals. Here the parametrization is for t between 0 and 2 pi, and our parametrization is cosine t, sine t, 0. So to take our line integral, we take our vector field, and then we dot with the velocity vector of the parametrization. So here, the velocity vector of cosine t, sine t, 4 is negative sine t, negative sine t, cosine t, 0. Now, the vector field is written in terms of x's, y's, and z's, but the integral is with respect to t, and here we need to replace each x with cosine t according to the parametrization. We need to replace each y with sine t according to the parametrization, and we replace each z with 4 according to the parametrization. Well, when we make those substitutions and we take our dot product, we end up with negative cosine t times sine of t squared plus 8 times cosine of t squared. And when we do some calculus here, we end up with 8 pi Newton meters as our work calculation. So here we'll have to do a little bit, this will require a little bit of effort from the calculus point of view. We'll need two integrals here, the first of which can easily be done with a u substitution, and the second of which we need to integrate cosine squared t, which you can either use maybe a trig identity if you remember it, or apply integration by parts, which is what I would probably do. What about the work done by this vector field on the bottom part of this surface? Well, now we're taking a line integral of the same vector field, but the parameterization is different. So we're still parametrized over the t between 0 and 2 pi, but now the velocity vector should be the derivative of cosine of negative t, which is sine of negative t, the derivative of sine of negative t, which is negative cosine of negative t, and the derivative of 0 is, of course, equal to 0. And now we're replacing all of the x's with cosine of negative t, all of the y's with sine of negative t, and all of the z's with 0. So when we make those substitutions and take our dot product, we end up with cosine of negative t times sine of negative t quantity squared. Here we can do a simple u substitution, and we find that the integral is equal to 0. So now we can use these two individual calculations to figure out the circulation of this vector field around this surface. Here, since we've parametrized in such a way that we respect the orientations, we know that we're simply going to add these two line integrals together. So our first line integral, we found that we got 8 pi Newton meters, and in the second line integral, we got 0 Newton meters, which means that the total circulation should be 8 pi Newton meters.